Now we're going to throw another little wrinkle into this method of integration by parts, which is the following. In some cases, integration by parts must be applied several times in order to evaluate a given integral. And several in this case could mean 2 times, it could mean 3 times, in principle it could mean 100 times. Now, of course, on a homework assignment or a final exam, we're not going to make you use integration by parts 100 times. But in theory, that could happen. And let's look at an example to see, well, why could that happen? How would that come about, and how would we deal with it if it does? And so I've chosen an example pretty similar to the one we just did in the last video. So we've got this time the integral of x squared times e to the 6x dx. And that seems like a good candidate for parts, because again, we've got a product here. And in fact, the way we would set it up, it seems reasonable that our conversation from the last video would also apply here. If we let w be x squared, that gets simpler when we differentiate it. And then if we let dv be e to the 6x dx, we can integrate that. We just need our pattern for linear composition. So let's do it that way. We'll use integration by parts with w equal to x squared and dv equal to e to the 6x dx. So then our dw is going to be 2x dx, and our v, antiderivative of e to the 6x, is 1 over 6 because of that pattern of linear composition, times e to the 6x. So we have that our original integral, the integral of x squared e to the 6x, that's going to be v times w, so 1/6, and I'll write x squared times e to the 6x, because we usually write polynomials before exponential functions, and then minus the integral of b dw. Well, we can simplify this a bit. 1/6 times 2 is a third. Of course, that being a constant, we can bring that outside the integral. But that still leaves me with 1/6 x squared e to the 6x minus 1/3 times the integral of x times e to the 6x. And now that is not an integral that I can just go ahead and directly integrate. That's not an elementary integral. In fact, now that looks a whole lot like the integral we just did in the first video for today. The only difference this time, we've got the x. It's multiplying an exponential function. We just have a 6x as the argument of the exponential function instead of simply x. But again, with our pattern for linear composition under our belts, that shouldn't really bother us. So one use of integration by parts wasn't sufficient in order to evaluate this integral, but it seems pretty clear that a second application of integration by parts should get us the rest of the way there. Now, when you recognize that integration by parts has to be used a second time, though, you do have to be careful in how you set it up, because you're now essentially bound by whatever your setup was from your first use of integration by parts. So here, the first time around, we let w be the power of x, and dv be the exponential function. We wouldn't want to switch that around this time, even if that seemed like a reasonable option. Because in this case, if we now let w be the exponential function and dv be the x dx, all we're actually going to accomplish is to undo our first use of parts. And we will wind up with the statement that the integral of x squared e to the 6x dx is equal to, wait for it, the integral of x squared e to the 6x dx. which is tremendously helpful. I know nobody would have guessed that that was a true statement. So that's why you've got to be careful when you're using integration by parts multiple times. However you set it up the first time, every subsequent time you set it up, you have to set it up the same way, or you're definitely not going to get anywhere with it. All right, so with that in mind then, we'll use integration by parts a second time. And so we got the W is going to have to be equal to X in this case, because of the fact that that came from what we let be W the first time around. The X came out of our original W, which was X squared. And dV is going to be e to the 6x dx, because that came out of our original dV, which in fact in this case it is the same thing. So dW then, the derivative of x is 1 times dx again is dx. And this step, the V is exactly what we just wrote down for our first use of parts. Again, that's 1/6 e to the 6x. So this gives the original integral now equal to, well, the first term, the 1/6 x squared e to the 6x, that just carries over, minus 1/3 times, it's the integral that we're now going to replace. That's what we're applying the integration by parts formula to. So that integral of x times e to the 6x, that again becomes v times w, 1/6 times x times e to the 6x, minus the integral of v dw, which in this case is just 1/6 e to the 6x times dx. And just like we saw in the first example today, now that is something we can go ahead and integrate. So first of all, let's simplify this. Get 1/6 x squared e to the 6x minus 1/18 times x times e to the 6x. And of course, that minus a third also applies here. So I'm going to multiply by the integral, and I'm going to bring that 1/6 out at the same time. So effectively, I'm going to have the minus a third times minus a sixth, which becomes plus 1/18 times the integral of e to the 6x. And that is an elementary integral. That's in fact the one we've done twice now, both of our dv's, computing that exact same thing. So that'll give us 1/6 x squared e to the 6x minus 1/18 x e to the 6x plus 1/18 times 1/6 e to the 6x plus c. And finally, we'll simplify. 18 times 6, that's 60 plus 48, that's 108. So we're going to get 1/6 x squared e to the 6x minus 1/18 x e to the 6x plus 1/108 e to the 6x plus c. So we're able to do it. It takes 2 uses of integration by parts, but we get there in the end. And you can imagine that if this had been an integral of x cubed e to the 6x, for instance, then that would have taken 3 uses of integration by parts. If it had been x to the 4th e to the 6x, we would have needed it 4 times, and so on. But what this does now raise the specter of is, well, how are you going to know when using integration by parts several times will work versus when it just means that integration by parts isn't the appropriate method and you're just going to go around and around and around trying parts again and again and again without any success. And so a good rule of thumb, once you've used integration by parts the first time, is to compare the new integral to the original integral. If that integral is getting better, as it did here, we went from x squared times an exponential function to just x times an exponential function, then keep going. Integration by parts is probably working out. On the other hand, if the new integral is actually worse than the one that you started with, stop right there. Maybe integration by parts isn't the right method. Maybe you need to change how you're assigning W and dV. But if the integral is getting worse, it's not going to get better, or at least examples of that would be exceedingly rare. Which does leave an interesting middle case. What if you apply integration by parts and the integral that comes out of it isn't better than the original integral, but also isn't worse than the original integral? Well, in that case, my advice would be try integration by parts one more time and see what you get. And if what you get out of that is something that you can work with, great, work with it. See if you can take that and finally evaluate the integral. But again, if you do integration by parts that second time, and it seems like, no, there's nothing I can do from here, then again, maybe integration by parts isn't working out, and you'll need to go back to the drawing board. So in our next video, let's see an example of exactly that sort of thing, and let's see if it is something that we can work with and ultimately evaluate the integral.